In this video, we are going to look at a new way to interpret an integral. The only way that we have interpreted it thus far is as the area underneath the curve. But in this video, we're going to explore the idea of the antiderivative as a way to calculate net change. So let's just pretend for a second that we have a situation where we have a garden hose dumping water into a bucket, a 5-gallon bucket, and as the water enters the bucket, the level of the water goes up. And let's go ahead and define S of t as the amount of water in the bucket at any time t. And let's also pretend that we know something about the rate of change of the amount of water in the bucket. Let's pretend that we know that the water from the hose is flowing in at a constant rate, and therefore the water height in the bucket is increasing at a constant rate. And let's say that that rate is 1.5 liters per second. And if I asked you how much water is in the bucket after 4 seconds, that would be easy to calculate. I know that after 1 second, 1.5 liters has gone in, so after 1 second I've got 1.5 liters. After 2 seconds I would have 3 liters. After 3 seconds I would have 4.5 liters, and then after 4 seconds I would have 6 liters. And this is easy to calculate simply by taking the rate, the constant rate, multiplied by the time, or in our case 1.5 by 4, in order to get 6 liters. In other words, I took S prime of t multiplied by the duration of the time, which was 4 seconds, and calculated my quantity of water that way. And let's pretend this time that there's some brat kid who's bending the hose and changing the flow rate of the water, so that S prime of t, or the rate of change of the water going into the bucket, is not constant. So sometimes it's 1.5, sometimes it's 0.2 liters per second, sometimes he pinches the hose all the way so that it's not touching, or so that the water is not going out at all, and it's changing, it's variable. I could still ask the same question, how much water is in at the time of 4 seconds, by accumulating all of the rates of change of water from the beginning at 0 all the way through to 4 seconds. So if it's flowing really fast at the beginning, I need to add all that up to, if it was really slow during the last half, I would add up those slow speeds. So I need to add up all the speeds that this kid is impacting, and I can do that with a definite integral from 0 to 4 of S prime of t. If I add up all of my rates of change in between 0 and 4, I'm going to be left with the antiderivative of S prime of t, which is S of t, between 0 and 4. And depending on what my function was, I would have S of 4 minus S of 0, and assuming that there was 0 water in the bucket at time 0, I would be left with an answer of just S of 4. So this is interesting. What I've said is that the total amount of water that is in the bucket is equal to the area underneath the curve of the derivative, or the area underneath the curve of the rate of change. If I integrate, if I integrate a rate of change I am informed in some way of what's going on with the original function. And if I'm going in between 2 points like 0 and 4, I'm finding the total change that has occurred between those moments. So let's go ahead and look at another example. Let's say that I have some object in motion, and I am going to look at the velocity of this object. This is v of t. So what I'm saying here is that as time ticks by along my x-axis, my velocity is going up. So this thing is going from a velocity of 0 to a velocity of 1. Let's say that this is equal to x. This is my line y equals x. At time 2, I have a velocity of 2. At time 3, I have a velocity of 3. So this thing is speeding up at a constant rate, 1 mile an hour, 2 mile an hour, 3 mile an hour, 4 mile an hour, 5 mile an hour, etc. It's increasing at a linear rate. So the question that I have is, what would I be calculating by calculating the area underneath the curve in between 0 and 3? What is this? What is the area underneath this curve? In other words, what is the antiderivative from 0 to 3 of Vt with respect to t? So if v of t is equal to x, let's just calculate this and then talk about what it is. I'd be anti-differentiating my function x. 1/2 x squared in between 0 and 3 is going to give me 9/2 or 4.5. So what on earth does this represent? Well, we already know the relationship between position, velocity, and acceleration, and we know that the derivative of position is equal to velocity, which means that if I were to anti-differentiate the velocity, if I go through my position or my order of position and velocity and acceleration, if this way is differentiation, this way would be integration. So the antiderivative of the acceleration would be the velocity. The antiderivative of acceleration would be velocity, and the antiderivative of velocity would be position. So what this thing is, this 1/2 x squared, this is in some way telling me about the position and the total position that has been changed between 0 and 3. And it just so happens that what 4.5 represents is the total distance covered by this object in motion within the first 3 seconds. If we're talking in terms of feet per second, this means that this object has moved 4.5 feet in a single second. And this might be more believable if we look at a simpler example where we say that the velocity is equal to a constant like 3. So if we look at the exact same scenario, and I want to find the antiderivative of this velocity function in between 0 and 3, in other words, I want to find the area underneath this curve between 0 and 3, this is going to give me 3x between 0 and 3, which is going to be 3 times 3, which is 9, minus 0. And it makes good sense that if I have a constant velocity of 3, I should say, feet per second, after 3 seconds, I will have traveled precisely 9 feet, right? After 1 second, if I'm going 3 feet per second, I will have covered 1 foot. And that's what would be represented by the area of this first little rectangle here. And then if I go another second, I've covered another foot. And then another second is a third foot. After 3 seconds, I'm sorry, I said that all backwards. I hope that wasn't too confusing. This has an area of 3, 3, and 3. When I was saying 1, I should have been saying 3. So if I'm going 3 feet per second, after 1 second, I've gone 3 feet. After 2 seconds, I've gone 6 feet. And after 3 seconds, I've gone 9 feet. So it's easy to see, it's easy to believe with a nice constant function. The same is true of a linear function like in this last example. All right, let's look at another example. And for all these examples, we're kind of looking at generic, general, non-specific functions just to try to develop this idea a little bit. But we'll try to put some more meat on these bones here soon. But if we look at this example of a velocity function that looks like this, I'm just going to call this area underneath this curve arbitrarily 3. So the area underneath the curve that is green is 3. And then let's say that the area underneath this portion of the curve is also 3, which is actually negative 3 because it's below the x-axis. And suppose I ask you to integrate from 0 to 6 this velocity function. You would have a result equal to 0 because you would have a signed area of 3 and a signed area of negative 3, which would result in 0. So we must ask ourselves, what the heck does this mean? And because velocity is directional, what this is indicating is that the total distance traveled from 0 to 3, or the net change in one's position, was 3 units, and then from 3 to 6 was 3 units in the opposite direction. So this answer of 0 indicates that our person is back at wherever they began. It means that their displacement is 0. They have traveled 0. They've covered a lot of ground, but they're back to where they've started. So this is like a person starting at home and walking to the store and then walking home. They covered distance both ways, right? On the way to the store, they covered 3 miles, and on the way back to the store, they covered 3 miles. So we don't say that that person walked 0 feet, but we do say that their displacement or their ending location is 0, if you will. It's where you started. But the question changes if I ask you, how far did this person walk? They walked 3 miles this way, and they walked 3 miles this way, so they walked a total of 6 miles. So what I'm getting at here is that there's a difference between displacement and the total distance traveled. This guy up here is the displacement. And if I'm interested in finding the total distance traveled, this is a little bit goofy, but what I've got to do is integrate from 0 to 6 the absolute value of my velocity function. I need to take this negative area and interpret it as a positive signed area. So for my example here, there's a couple of ways to do this. The best probably being that I would want to integrate from 0 to 3 my velocity, and then I would want to add the integral from 6 to 3 of my velocity as well. The reason that I want to go from 6 to 3 is because by reading this backwards, my negative signed area becomes a positive area, and this would generate my answer of 6. So in this case, knowing something about the graph becomes really necessary and convenient. So let's just write down this observation a little bit more formally. If I integrate the velocity from time 1 to time 2, t1 is a starting time and t2 is an ending time, I'm finding the displacement during that time interval between time 1 and time 2. So I'm finding, like, again, if we've got a little person and they go 20 miles this way and then they come back 12 of those miles, I have a displacement of 8 miles. This is how much they ultimately have been displaced or moved. So their ending position is 8 miles away from wherever they started. And this is different than the total distance traveled. The total distance traveled would be the antiderivative of the velocity from time 1 to time 2, only I would need to take the absolute value so that I could interpret this area and this area as both positive distances traveled to get my answer of 32 miles traveled for this little picture.